Good afternoon, guys. Man, my hair looks terrible. Too much of it.
How did you want us to submit the 2 assignments? Just take pictures of our work and send it through, or?
Jyotika, did you say something?
Yeah. Am I on mute? I don't know. I was just asking if the 2 assignments, like, how did you want us to submit it?
However, it will let you. If you have a Word document, that should easily be able to submit it, or a PDF could be submitted, or a picture could be submitted.
Okay, cool.
Those are all sorts of different ways as well that you'd be able to submit your answers during the AP exam.
Yeah. Okay, cool.
So while we're waiting for everyone to join, I'll tell a quick funny story that happened to me recently. Well, in my townhome complex, there's this neighborhood cat that just hangs out. We assumed it belonged to somebody years ago, but the person we thought it belonged to never. They left, and so now we have no idea who it belongs to. I guess it's homeless. But I'm not really a cat person, more of a dog person. I'm not mean to it or anything, or overly nice to it either way. But recently, we've had beautiful weather, and so I've left my door open sometimes, or just hang out on our small backyard on the porch sometimes. And one time last week, the cat just walked into my bedroom. I left the door open. I could never have imagined that would have happened. The cat just walks into my bedroom. So been more colorful about that recently, but also it now will not leave. That cat will not leave. It just hangs out on our porch all the time now, sitting in my lawn chairs sometimes.
You should keep it.
I don't really want to keep it, and the biggest reason, next part of the story, why I don't want to keep it, I think I'm just now discovering that I'm allergic to cats. I've never really been around cats very much before, and now that cat will not leave over the past week. And
hello.
what is this?
I use.
Hi, Logan.
And with that cat around all the time, my eyes have been itchy, watery, and red lately. I've had to take some Benadryl and eye drops. I think
Coronavirus symptoms.
They
Bro,
are
my
those are
grandpa
not
had a
coronavirus
cat,
symptoms.
and he got a cat so he can kill the mouse, like mice. But the cat wasn't killing mice, so he killed the cat.
What?
So you should kill the cat.
Oh God. That's a little dark.
It took a turn, a big turn.
Yeah, I was just saying I want the cat to leave because I think I'm allergic to it. You want
You should kill the cat.
Yeah, you should do what Zeus did.
Definitely not. My mom suggested spraying water on it. Not hurting it at all, but it'll make it mad.
I like your glasses, Mr. Hunter.
Thank you. Had to wear them more lately though, because of my eyes being irritated.
Because of the cat.
Yeah, I think so. I think it's because of the cat. If it's not, I have no idea why.
Mr. Hunter, what time do you wake up at?
Depends. Generally, my sleep schedule recently has been like midnight to 8. Yeah, but sometimes it translates, and I'll go to bed even later and wake up later. Because there were some days over the past few weeks that me and my roommate and some other friends were playing Catan online, as I mentioned, and we just stayed up super late playing. As we continue waiting, another cool thing for me recently, I now have a girlfriend. We actually started dating instead. We started dating back at the beginning of February. It's been a little difficult having to date and see each other mainly through Zoom recently, but it's going really well, and it's been really good.
Go visit her.
I will this weekend. Tomorrow is actually my birthday, as I think I mentioned. Sunday is her birthday, so I'm gonna go visit her this weekend.
Oh.
I can't think of any calculus meme ideas.
Well, no, it should be a romantic calc meme.
Or the cat calc memes.
I mean, you could get some ideas if you just search some. There's tons of calculus memes. Or as I said, it doesn't have to be about calculus if it's about our class.
Where's Adam when you need him?
When Mr. Hunter finishes explaining something after the bell, and he turns around and no one's there.
Yeah, something like that. Something about like the behavior of our class. That'd be entertaining.
You want us to post them on Classroom?
Sure, email it. I'll send them out.
Put them on Classroom so we can all see them.
No, I think it was.
Yeah, anyone who makes them or finds them. I mean, you could just take somebody else's, but preferably one I haven't seen before. But yeah, just post it on the Google Classroom in the stream. Start some comments about math memes.
We just talk about memes instead of review.
No, we should review. Well, it's 1:05 now, so let's begin. If anyone else joins, I'll admit them like usual. Okay, so I'm gonna try this a little differently today. Go here. Okay. Let's put this down there right now. Okay. So got this slide, some exam info. AP coronavirus updates at collegeboard.org. That's where you can find tons of info. I've already mentioned a lot of the info, but that's way more detailed right there, straight from College Board. As I've said before, your exam is now Tuesday, May 12th at 1 p.m., just a week later than before. If that doesn't work for some reason, makeup exam Monday, June 1st at 3. As mentioned before, the exam now is online, 45-ish minutes. 2 free response questions. Question 1 is going to be 25 minutes with a 5-minute upload time and worth 60% of the points. Question 2, 15 minutes with a 5-minute upload time worth 40% of the points. It is essentially an open note, open book, calculator allowed but not required test. I mean, because they can't stop you from looking at notes or your books or using a calculator if you have one. So that's why all of those are definitely allowed. But equitably, calculator is not going to be absolutely required. Just because, I mean, not everyone has a fancy calculator at their house. So most of the questions will probably be maybe more the kind that you would see on a non-calculator section of free response. You can use a computer, tablet, or phone, like some of you may have done for the assignments this week or in AP Classroom. You will be able to do the work on like your own sheet of paper and then take a picture of it to upload. Okay. So let's go to the humongous review sheet. I've got some of it already written down. We're going to units 5 and 6 right now. Unit 5 is heavy on function analysis. And my handwriting, I was writing on my computer with the touchscreen, so it looks a little weird at some places. So if f is continuous and differentiable, then f prime c equals f b minus f a all over b minus a. That looks like a negative a. I'm going to rewrite that so you don't think it's a negative a. Okay. So that should just say f. Oh, that's a really thick pen. Put that down there. Yeah. And so essentially what mean value theorem says is that the average rate of change or slope of the secant line over the whole interval, which is the right side of my equation, at some point in the interval will equal the instantaneous rate of change or the derivative at some point in the interval. So the average rate of change over the entire interval will equal the instantaneous rate of change at some point in the interval, or the slope of the secant line from the beginning point to the ending point of the interval will equal the derivative at some point on the inside of that interval. And then Rolle's theorem is just a special case of that. That if it's continuous and differentiable and f of b does equal f of a, well then if we plug that idea into the mean value theorem equation, we then automatically get f prime c does equal 0. Oh, I just figured out how I can see the chat while I'm sharing my screen. Okay. Yeah, Logan, you're right. As I posted earlier, no more school for the rest of the year. Okay, continuing. Extreme value theorem, just, it's not really a formal definition I have here, but it's essentially that if you have a function that's continuous on an interval, there will for sure be an absolute max at some point and an absolute min at some point. That's what this says. There will be an absolute max and an absolute min at some point in the interval. And other than going over units 5 and 6 on the review sheet, I'm going to go over one of the free response questions that you need to do for next week, just so you see how all of these kind of things can go together, and there will be a mean value theorem question on that. And so absolute max and absolute min, how you might word it is that f has an absolute max of f of e at x equals e. I said this based on my picture I have over here. So I have these dashed black lines showing the beginning and ending of the interval. And so the highest part is when the purple function is at x equals e. So then f of e is the absolute maximum value. The absolute max, if you're asked what is the absolute max, that's asking for the function value, the y value. And if they wanted the x value, they would say, what is the x value of the absolute max? But the best way would be just to list the whole thing to guarantee that you answered what they're asking for. And then in this picture here, not only is the point where x equals b the relative minimum, it is also the absolute minimum because it is the lowest value the function ever attains in this entire thing. And if we took off the black dashed interval lines, it would also be the lowest value the function ever attains. I mean, assuming the purple function goes on forever in either direction that way. F of b is also the lowest it ever attains from positive infinity to negative infinity. So even if we didn't have an interval, f of b would also be the absolute minimum. And so we can say that f has absolute minimum of f of b at x equals b. Then f of b, at x equals b and at x equals d, those are relative minimum values. At x equals c, that's a relative maximum value because it's the minimum just in that region, or it's the maximum just in that region. Critical values, this is critical point, but we called it critical value, is x equals c could be a critical value if f prime c either is 0 or f prime c does not exist. So I tried to draw that here, that up here we have a maximum, that point, f prime c would equal 0 because causing a horizontal tangent. This is also a horizontal tangent, so f prime c equals 0. And then I tried to make it look like that's a vertical tangent line right there. So f prime c would not exist right there. So those are some different examples of where a critical value could be. Going on to the second half of that page. Signs of f prime. Well, if f prime is positive, that means f is increasing. If f prime is negative, that means f is decreasing. If f prime of x equals 0, then that's a critical value and maybe a max or a min. First derivative test. That looks weird. I'm gonna rewrite that. If at x equals c, f prime of x switches from positive, this is meaning to be a positive, to negative, then we have a relative max at c. And then the other way around, if at x equals c, f prime of x switches from negative to positive, then relative min at c. And you can use the at sign in your answers. I feel like that's a universal symbol everyone knows. The positive and negative symbol are perfectly allowed when doing this reasoning on the AP exam. Question 9, what does the signs of f double prime represent? Well, f double prime, if it's positive, will mean it's concave up. Concave up also means that slope is increasing. I'm gonna add that in here. concave up also means that the slope is increasing. Slope is increasing, concave down would mean slope decreasing. And where something switches concave, should be an E on slope. There we go. And where a function switches concavity, that is a point of inflection, as it says in D, a point where f of x changes concavity, that's a point of inflection. So we've got this picture here. Left side, it's concave down. We have super steep negative slope, and then it becomes less and less and less steep, meaning the slope is increasing. And until right here, the slope is 0. And then changes to concave down, and slope starts going back that direction again. But so back to being more and more and more negative. So then the slope is decreasing here. So the slope was increasing, and it definitely looks concave up like a cup here, and looks concave down like a frown here. But also the slope is decreasing in that region. Okay, and then 11 says what is the second derivative test. Second derivative test. Both first derivative test and second derivative test are looking at figuring out if something is a minimum or a maximum. They're both looking to figure out if something's a min or a max. And second derivative test starts off given that if f prime of c equals 0. So if you already know f prime of c equals 0, then you check the second derivative to see what's happening where f prime of c equals 0. And if f double prime of c is positive, well, that would mean concave up. That's what I mean by this right here. Concave up, cc up, concave up. That's what that is representing. And so if f prime of c is 0, meaning we have a horizontal tangent there, so we have a horizontal tangent there, and it's concave up, well, then it would have to be a relative minimum at that point. So that's what the second derivative test says. Or if we already know f prime of c is 0, meaning we have a horizontal tangent there, and f double prime of c is negative, or concave down. So we have a horizontal tangent where it's concave down. Well, that would mean that we have to have a relative max there. And so that's what second derivative test says. On number 12, I don't really have enough room to do an observation problem, or I have one plan to go over now. I would suggest looking at your notes, and we will probably see at least one amongst the free response questions that we go over in the next few weeks. So in the key for this humongous review sheet that I post, I'll list steps. I'll list the steps for an optimization problem in the key that I post, and we'll see an example of doing one amongst some of the free response questions that we do. Good. Unit 6, integration and accumulation of change. So first, a Riemann sum. Riemann sums, you're essentially summing many, that should say n, summing n. This is an n. Sum n many rectangles. I don't know what that is right there. There we go. Summing n many rectangle areas underneath a function. And so generally with a Riemann sum, it would look like this, where f of x sub I times delta x, that represents the area of one of the rectangles, where delta x is the width of one of those rectangles, f of x sub I is the height of one of those rectangles because it's the function value. And just for each iteration, I would represent which rectangle you're on. N is the number of rectangles just for each iteration. That tells you where you're going. You might evaluate it at the left endpoint of each interval or the right endpoint or so on. And after I go over unit 5 and 6 on this review sheet, we're going to do one of the free response questions that are assigned for next week. And so we'll practice with a Riemann sum. We'll practice with mean value theorem. There's a lot of concepts in the free response question we're going to go over. Exact area, though, well, a Riemann sum in general is only an approximation or an estimate. Even with like 100 rectangles, there's always going to be some piece that's a little overestimate or underestimate when dealing with a Riemann sum. And if we want an exact area under that curve, then we would need to take essentially infinitely many rectangles. And so that's what this is right here, the limit Riemann sum. The limit as n approaches infinity, because n is the number of rectangles. Limit as n approaches infinity, the summation of all of the rectangles, where delta x is b minus a over n. And so if n is going to infinity, that delta x is also approaching 0 as well. So, and this exact area of a limit Riemann sum is also what a definite integral equals, such that the limit Riemann sum equals the integral from a to b of f of x dx. Then first fundamental theorem of calculus. Guarantee you the two different fundamental theorems of calculus will for sure be on the AP exam in some way, because it's a calculus AP exam. So first fundamental theorem of calculus, given that capital F prime of x equals lowercase f of x, that would mean capital F is the antiderivative of lowercase f. Then the integral from a to b of f of x dx equals the antiderivative at b minus the antiderivative at a. So that's essentially just first fundamental theorem of calculus essentially just tells that we can do definite integration, One other way to write this one that is helpful depending on the kind of things you have is I can throw capital F of a over to the other side, and it could look like capital F of a plus integral from a to b of f of x dx equals capital F of b. And so the integral from a to b of f of x, which represents the area on the curve, that's also the displacement of something. That's the change over time. That represents the that's the accumulated change over time. So the integral from a to b of f is the accumulated change starting at a and ending at b. Capital F of a is the starting point at a. So if you just add your beginning amount plus your changed, how much you changed, you would get your ending amount. Second fundamental theorem of calculus says that if we take the derivative of an area function, we get the original function. So we have integral from a to x of f of t dt. That is, I called it an accumulation function. I also called it an area function because that's what it represents. It represents the area under f between some given value a until you get to x. And if you take the derivative of this area or accumulation or integral function, you just get the original function. Okay, and then one other thing about is some of the properties of definite integration. That the integral from a to b of f, you can flip the limits and then throw a negative in front. That works. Or also the integral from a to b of plus the integral from b to c. Well, those can be combined, and you have the integral from a to c of f. Okay. And the second half of that page, the integral from integral of f dx. Well, they're just asking about indefinite integration here. The integral of f dx is just the capital F of x plus c, where capital F in all of this is representing the antiderivative. Capital F is representing the antiderivative. Powerful for integrals. I mean, again, most of this stuff you should already know. You should have been able to fill out some of this on your own. Integral of x sine of x squared. That doesn't look like an x. I'm gonna add that in. There we go. Okay, integral of x sine of x squared dx. I thought just doing an example was the best way to remind you about U substitution, so we'll do a quick example of that. Generally, U substitution, you want to pick U to be something that's inside of a parentheses. U substitution is essentially reverse chain rule. It's essentially reverse chain rule. So if you think of it as reverse chain rule, I mean, you wouldn't have to formally do every step all the time if you know how to undo what has happened. Because I mean, in chain rule, you got to multiply by the derivative of the inside. So if we're reversing it, we need to divide by the derivative of the inside. So I can see derivative of the inside is x. The inside is x squared, so the derivative of the inside is 2x. So somehow we'll also end up dividing by 2x. So you could think of it like that, but to formally remind you how to do U substitution. Okay, so U equals, how we're going to have it be x squared, and then du equals 2x dx. Okay, and since we want what's inside the parentheses to be u, we also want to replace anything else that also has x. So x and dx, those are going to be, those need to somehow be replaced. Those need to somehow be replaced. And I can get those by themselves right here by just dividing both sides by 2. So we have x dx equals 1/2 du. And so that x dx, where I've underlined in red, will get replaced by 1/2 du. I'm going to pull that 1/2 out front. 1/2 integral of sine of u du. Okay, now we'll still have 1/2 integral of sine, or antiderivative of sine, is negative cosine. Negative cosine of, let's go ahead and plug u back in, so put x squared in there. And plus c. Don't forget your plus c, that would be bad. Okay. I'll provide an example of 11 and 12 when I put the key up. I don't want to go over that right now. But let's look at some of the BC only stuff right here. Integration by parts. Integration by parts. And we'll do another example of this when I go over the free response question we're going to do later. But the formula for integration by parts, hopefully you remember, is it the integral of u, that's supposed to be u, got a little tail on it, u d v equals u v minus the integral of v du. Okay, and it is essentially the reverse product rule. It's essentially the reverse product rule. If U substitution does not work, and you have a product of two things, then you would want to try integration by parts. If U substitution does not work, and you have the product of two things, try integration by parts. And when doing integration by parts, we would need all of these pieces. We would need u, we'd need dv, we'd need v, and we'd need du. The original function that you would be trying to integrate would look like the left side. So meaning you already have u dv, and with u, you need to figure out what du is, meaning you would have to take its derivative. And with dv, you need to figure out what v is, meaning you would have to take dv's integral. So since du has to get integrated again later on, you want to pick something for u that gets simpler when you take its derivative. You want to pick something for u that gets simpler when you take its derivative. dv just cannot get more complicated when you take its integral. dv cannot get more complicated when you take its integral. Ideally, they both get simpler when you do the things you have to do. The dv, when you take its integral, it gets simpler. U, when you take its derivative, gets simpler. That's ideal. But as long as dv doesn't get more complicated when you take its integral. Then 14, an example of integration by partial fractions. Well, generally, a very general example, you'd have something that's a fraction that could be factored on the bottom. You have something on the top, maybe a number, maybe something with an x, some linear function on top, and some linear stuff, maybe quadratic or cubic or something on the bottom that could be factored, such that it could be split up by partial fractions to be something over one of them put a capital A plus a capital B over the other one, where something with an x is down here and something with an x is down here. And now when you take the integral of this right side, you'd end up with a natural log of this bottom plus a plus b natural log of this bottom, something like that. The partial fractions is necessary here because like you probably wouldn't have a rule for what's happening right here. If the top is something squared and the top, and if the bottom is something with a squared and the top is just a number, then U substitution wouldn't work. And we have lots of notes of this kind of stuff. Improper integral. Something is improper if limits of integration should be no. Are positive or negative infinity or discontinuous. So if the limits of integration are positive or negative infinity or discontinuous, that would make something an improper integral, And when doing an improper integral, you have to have limit notation. You would have to have limit notation. And we will see some of that. Some of those will get done. Some of the free response questions that we do from time to time. And then 16 is related to 15. Saying what does it mean for the integral to converge or diverge? So it will converge if that limit actually equals some numerical value. It will converge because if we use limit notation, then that would mean like limit as a b approaches infinity of the integral from a to b of f. If that equals some actual value, then it would converge. But if it equals positive or negative infinity, like just keeps adding forever or keeps subtracting forever, then it would diverge. Okay, so that's some of units 5 and 6. We'll go over some of units 7 and 8 next Wednesday. But right now, I want to go over one of the free response questions that you have to do for next week. It's a really good one. That guy that makes them that we're going to do, he's made lots of questions. He's a very good teacher. He's the one making all the free, doing some of the videos of the YouTube channel that I keep suggesting for you to watch. And it's, so we're going to look at the free response questions from Passwater, the ones that are not the 2016 free response questions. So in next week's assignment, so we're looking in next week's assignment, I have 2 different files. One of them is the 2016 BC free response questions. The other file says BC 1 through 4, 2020. We're going to look at question 1 from that. And so in this question 1, we have a lot of stuff happening. They gave us a table for G and G prime, and we're told F and G are both twice differentiable. And then they gave us what F is, that F is 2 plus the integral from 0 to 3x of G of t dt. Okay. Interesting. So first, we are asked to explain why there must be, right there. Explain why there must be a number C somewhere between 0 and 9, such that G prime of C is 1/3. So G prime of C is 1/3. Okay. Well, that sentence right there, I'd hope to you sounds kind of like mean value theorem, because they have an interval right here from 0 to 9, and we're told here we want to show that there is for sure some value between 0 and 9 where the instantaneous rate of change, g prime of c, does equal the value 1/3. And mean value theorem says that the derivative at some point in the interval will equal the average rate of change at some point in the interval, meaning this g prime of c equaling 1/3 will equal g of b minus g of a over b minus a for some a and b. Sadly, though, I don't think it's actually the entire interval 0 to 9, because if we were to start plugging some stuff in here from the table, g of 9 is negative 1/20th, and g of 0 is negative 2. And if I subtract those, that doesn't turn out nicely. We need it to somehow end up being 1/3. So we just need to pick some interval amongst the table that they gave us, such that if we just found the slope between 2 points, it is 1/3. Because mean value theorem says that the derivative at some point between 2 points will equal the slope over those between those 2 points. So if we see some spots here such that the slope is 1/3, then that's what we want. So we want the y value to go up by only by 1 for every time the x value goes up by 3, because that's what a slope of 1/3 would mean. And so if we look right here, that's what's happening between these 2 points. From 0 to 3, x goes up by 3, while the y value goes up by 1. And if we actually write that in, move that back over there. Then g of 3 minus g of 0 over 3 minus 0, well, that would be negative 1 minus negative 2 over 3. Well, that's really a plus 2. Negative 1 plus 2 is 1, so 1/3. So from the interval 0 to 3, the average rate of change is 1/3. So by mean value theorem, g prime of c will equal 1/3 for c in the interval 0 to 3. Because from the interval 0 to 3, the slope over that interval from 0 to 3 is 1/3, and by the mean value theorem, the slope of the whole over the whole interval will equal the instantaneous rate of change at some point in that interval. So that's a reminder of how we can use mean value theorem. And then part B. Part B.
You have to state that it's continuous in order for mean value theorem to work.
You are right. I should have mentioned that. Do we need to state that it's differentiable?
No, because it's given.
No, they already told us that. And why do we know that it's continuous?
Its differentiability implies continuity.
Yeah, because it's differentiable. So the best way to explain that is just somewhere in the problem say because differentiable g of x is continuous, something like that, somewhere that just say it's continuous because it's differentiable, and then we'd be good. But yes, you're right, we did need to include that. Okay, on B, we are asked to evaluate integral from 0 to 3 of 40x f triple prime of x. Wow, we don't have an f triple prime somewhere. They gave us f though. They did give us f. But even if we found f triple prime, we have two things multiplied together. I don't have a function inside of a function here. If we had a function inside of a function, we could do u substitution. We have 40x as one function. We have f triple prime of x as a different one. So which formula or process would we want to do to integrate something when two functions are multiplied?
Integration by parts.
Yes, by parts. So we're going to use by parts here. And again, we want to choose the thing to be u such that its derivative gets simpler. And our two different things, we have 40x and we have f triple prime. So which one would end up being u?
40x.
Yes, 40x is going to be u. So we're going to have u equals 40x, which would then make dv equal to f triple prime of x dx. Okay, now let's figure out the other pieces. Well, if u is 40x, du is then 40 dx. And if dv is f triple prime of x, to get v, we want to take its integral. Well, what would be the integral of f triple prime?
F double prime.
Yeah, f double prime. Yeah, we're just going back. Integration is going backwards, and so we're just taking go backwards there. Antiderivative. That'll be f double prime of x. Okay. Well, that should make it a little simpler. Okay, now as we start writing it, I'm going to drop the limits real quick until we have the answer. So we're doing now this whole thing, the integral of 40x of triple prime of x dx based on integration by parts. That will equal u times v. So 40x of double prime of x minus the integral of v times u. I'm sorry, u dv. Wait, u dv, no, v du. V du, yeah. Which would be 40 f double prime of x dx. Okay, and so we have 40x f double prime of x minus, well, what is the integral of 40f double prime going to be?
40f prime.
Yeah, 40f prime. Okay, then I'm gonna put my bracket on there and say that that's now from, I'm gonna add my limits back. Let's say the integral from 0 to 3 of 40x f double prime of x, no, triple prime of x. Dx. Okay, so for integral from 0 to 3 of 40x f triple prime of x would equal 40x f double prime minus 40f prime, evaluated from 0 to 3. Okay, one problem. So we will now have to plug in 0 and plug in 3 and subtract, but we need to know what f double prime is and what f prime is. Okay, so let's go back up to the top to figure out what those are. Oh, I don't need to go back up top. It's F's right there. Okay, so they gave us f right here, and we need to figure out what f prime is. So we would be taking the derivative of this whole thing here. Well, derivative of 2 is 0. So then we're taking the derivative of this integration. See, this is a highly likely kind of problem. It's involving so many different things. It's involving integration by parts. It's involving if you can do definite integration. And then right now, we have to take the derivative of this twice. So it's involving, if you know how to first take a derivative, it's involving chain rule. And because we're taking the derivative of an integral, it's involving if you know how to do fundamental thermocalculus. So that's the kind of questions that might end up this year, where just one part will encompass so many different concepts. So the derivative of the integral from 0 to 3x of g of t, well, that will be g. When we take the derivative of the integral, this 3x will go inside there, and we have to multiply by the derivative of that's going inside there because of chain rule. So we will end up getting g of 3x times 3. So that right there, that is f prime. And then take the derivative of that because we need f double prime. So we're taking the derivative of this. Well, that'll end up being, because of chain rule, that'll be derivative of the outside, so g prime of 3x times the derivative of the inside. So that 3 that's on the outside now gets multiplied by 3, so we have 9g prime of 3x. Okay, so now we know what those are. And if I was to start evaluating this, plugging in 3 now. So 40 times 3, well, that'll be 120, times f double prime of 3. F double prime of 3, that'll be then, I'm going to put that whole thing in parentheses, 9g prime of 9g prime of, that would end up being 9. Minus 40. Then f prime of 3. F prime of 3. That would be 3g of 9. Okay, then minus, put bracket around this whole part that's being subtracted. Now we're plugging in 0. Well, if I plug in 0 to this term, that will just end up being 0. Okay, then plug 0 into this term right here. That will end up being 40 times 3 g prime, 3g of 0. Okay, so we need to figure out what g prime of 9 is, g of 9, and g of 0. Did they give it at us at top? Yeah, they did. Awesome. So g of 9 is negative 1/20th, g prime of 9, 3/4. So this right here, minus 40. Well, I'm going to multiply. Go ahead and multiply by the 3. So 120 g of 9 was the negative 1/20th. 120 times 9 times g prime of 9. What was that? 3/4 times 3/4. Okay, then that will be plus 120 g of 0. Let's see, what was g of 0? Negative 2. Could we stop right there?
Yes, we could.
Yes. Yes, we could. We could stop right there. That is perfectly fine on the AP exam. Feel free to stop. Once you have something that is all numerical that could just be plugged into a very simple scientific calculator, you could stop right there. We've got 120 times 9 times 3/4 minus 120 times negative 1/20 plus 120 times negative 2. That I could just plug it into the calculator, a simple scientific calculator, so you could stop right there. You could also keep going. And if you do keep going, I don't remember the final answer and didn't already write it down. Let's see what was it? It ends up being 576. Oh, nice. Nice even number. So if you do go, you do continue on, yeah, that's what you would get. Okay, well, let's go to part C. Okay, still on my table here. Part C is using a right Riemann sum with 3 subintervals. Okay, so we're using the idea of Riemann sums. We're asked to approximate the length of the curve of g of x from 0 to 9. Ooh, so it's also going to involve arc length. Well, this is not the kind of arc length we talked about right before spring break. We talked about that in several different ways because that was with parametric and vector equations. This is the kind of arc length from back in January with rectangular equations, where the integral from a to b, the square root of 1 plus f prime of x squared dx. That right there is the formula for arc length. We should have a equals capital L there, maybe. That is the formula for arc length. Integral from 0 to b of the square root of 1 plus f prime of x squared dx. So we're wanting to approximate it though. So from 0 to 9. So we're doing the L. If we were to actually do the integration, if we actually had a function, we would do the integral from 0 to 9 of the square root of 1 plus, well, this is g, so it'd be g prime of x getting squared dx. But we don't have a g function or a g prime function to really be able to plug in there and get what that actually is to actually be able to take this integral, which is why we need to do a Riemann sum. So we're just going to approximate. So I'm going to put a little approximation symbol there. And if we're doing a Riemann sum, we're going to do 3 subintervals just because that's, how they have things separated here. So starting here until here. Okay. Well, this will look a little different than some of the Riemann sums that we did. The Riemann sums that we did, we were adding up rectangles to get the area under the curve. Instead of adding up rectangles to get the area of the curve, we're going to be adding up these. Well, remember what that dx represents. That dx, it's an extremely small change in x. It's a really small change in x. It's a change in x as the number of rectangles goes to infinity. Well, or in this case, as the number of arc lengths, little tiny arc length segments goes towards infinity. So in this case, since we're doing a Riemann sum, that dx, it's still going to represent the change in x. It's still representing the change in x. Just instead of doing infinitely many arc lengths from 0 to 9, we're only doing 3 arc lengths from 0 to 9, where that dx represents the width each time. So for the first subinterval, our width is 3, because we're going from 0 to 3. Then times this whole piece here, integral, no, not integral, square root of 1 plus g prime of x squared. Notice they said a right Riemann sum. What do we need to plug in for x if we're doing a right Riemann sum?
3.
Yeah, we're going to plug in 3 for x for the right Riemann sum, meaning this right here needs to be g prime of 3 getting squared. And then we'll add it for the next interval. It'll the width of the next interval, we're going from 3 to 5, so the width of the next interval is just 2 square root of 1 plus g prime of, now it's going to be g prime of 5 squared. And then for the last interval, from there to there, from 5 till we get to 9, that width is 4 square root of 1 plus g prime of 9 squared. Okay, well, we can't leave that like that because we got some function notation inside there, so we need to plug some stuff into that. So again, we have 3 square root of 1 plus, well, what is g prime of 3? G prime of 3 square root of 8. Well, then that needs to get squared, so then that is 8. Ooh, that turns out nicely. 1 plus 8 is what?
9.
9, and square root of 9 is 3, and then 3 times 3, this entire thing right here ends up being 9. That's nice. Okay, then let's figure out what that next term is. We have that 2 square root of 1 plus g prime of 5 squared. G prime of 5 is square root of 3. Well, square root of 3 squared is just 3. So right here we have 1 plus 3, which is 4. Square root of 4 is 2. 2 times 2, we end up with 4 right there. That worked out nicely. Okay, then we have plus 4 square root of 1 plus g prime of 9 squared. G prime of 9 is 3/4. 3/4. So we're going to have 3/4 squared right there, which would be 9 over 16. Okay. Well, that didn't work out as nicely. But could we have stopped right there? Just have 9 plus 4 plus that mess in blue right there? Could we stop there?
Yep.
Yeah, we could. So if we don't really want to put forth these first two terms were easy to simplify. So that wasn't a big deal. But this last term, maybe you don't automatically see how you would simplify it. And so you could stop right there if you want to, and that'd be perfectly fine. But one way you could go on, if we combine fractions, what is 1 whole plus 9/16? Well, I could call that 16 over 16. Well, 16 plus 9 is
27.
what?
27.
Nope. 16 plus 9 is
25.
25.
25.
There you go. So that means that we have 25 over 16, and we're taking the square root of that. Well, 25 over 16 square rooted would end up being 5/4. So this would be 4 times 5/4. 4's cancel. We just have 9 plus 4 plus 5, which is 18. So 18 is the approximation for that arc length. So that one problem showed both our understanding of the arc length formula as well as understanding of Riemann sums. And next, Taylor polynomials. Ooh. Hopefully you remember this from our week of distance learning, Taylor polynomials. So we're asked to let p sub n of x denote the nth degree Taylor polynomial of f. Okay. They want it to be centered about x equals 0. Well, if we have a Taylor polynomial centered about x equals 0, what else could we call that Taylor polynomial?
Maclaurin.
Oh, Maclaurin polynomial. Well, we have p sub 2 of x, meaning they want a second degree Taylor polynomial. They want a second degree Taylor polynomial. And so let's go ahead and write down that formula of what that would look like. P sub 2 of x. Okay, well, the first term would be f of 0, because it's going to be f of c times x to the 0 power over 0 factorial. A whole bunch of zeros in that. Then plus the next term would be f prime of c. Well, this c is 0. Then times x to the first power over 1 factorial. I don't need to put over 1 factorial because that's redundant. Then plus the second derivative of f at 0 times x squared over 2. And really that's a 2 factorial, but 2 factorial is 2. Okay, so that's the formula that we need to go by. And so we're going to need f of 0, f prime of 0, and f double prime of 0. And I didn't copy f's equation onto this page. Oops. Okay, well, f of 0, if we go back and look at the previous page. Oops, clicked on the wrong one. Okay. F of 0. Well, we have f of x equals 2 plus the integral from 0 to 3x of g of t dt. So f of 0 would mean 2 plus the integral from 0 to 0 of g, which, well, integral from 0 to 0 would just be 0. So f of 0 is 2. F of 0 is 2. So that is helpful. Let's go back to the next page. Write some of that down. We just got the f of 0 is 2. And I'll move this back over there. F prime of x. What did we say f prime of x was? F prime of x was 3g of 3x. And so then f prime of 0 would be 3g of 0. Well, g of 0 is -2, so 3 times -2, that's going to give us a -6. Okay. And we also need f double prime. What was f double prime on the previous page? F double prime 9g prime of 3x. Okay. F double prime of x is 9g double prime of 3x, meaning f double prime of 0 would be 9g double prime of 0. G double prime of 0 is 4. So f double prime of 0 is then 36. Okay, so we got those pieces. Now we can just formulate our equation, just build it and put it together. So p sub 2 of x, which means the second degree Taylor polynomial of our f of x function centered at 0, is going to be first f of 0, which is 2, plus f prime of 0, which is -6, times x. Oops. What? There we go. Then plus f double prime of 0 over 2 times x squared. Well, f double prime of 0 over 2, f double prime of 0 is 36, over 2 is 18, so plus 18x squared. And there we go. Right there in blue, that is our final answer. That's the second degree Taylor polynomial of f centered at x equals 0. And one last problem they're asking us to do. E says, now consider the geometric series, the sum from 0 to infinity of a times r to the n power, where the first 3 terms are the polynomial we just got. And if you ever had a problem like this, you could get part E right with getting part D wrong, as long as you did the part E's process based on your answer from part D. They look at that, just like I would when grading. We're asked to find the sum of the series when x equals 1/6, or show that the series diverges, Okay. Well, first off, if our series is representing this, as those are the first 3 terms, then that means we have the sum from n equals 0 to infinity of a r to the n power, that is supposed to equal 2 minus 6x plus 18x squared. Then there would be minus something, then plus something. Those are just the first three terms of some geometric series. We are asked to find the sum of a geometric series, so let's remind ourselves real quick what the formula for that would be. The sum of a geometric is going to be a over 1 minus r. A over 1 minus r. Okay. And the r is whatever it's multiplying by each time. R is whatever it's multiplying by each time. What do we multiply 2 by to get negative 6x? What do we multiply negative 6x by to get 18x squared, and so on? And that would be the r.
Negative 3x.
Yeah, negative 3x. So r, we see here, is negative 3x. Okay, that's awesome. And now they want to know what the sum will be when x is 1/6. So that means more formally, the r in this scenario is going to be, let me write that somewhere. I'll just scroll down and give myself a little more. Here we go. So then r is going to be negative 3/6, putting that 1/6 in the x spot, or negative 1/2. Okay, so now we know what the r is for this geometric series when x is 1/6, and for a geometric series, this r is currently, well, the absolute value of it is less than 1. So does that mean this will converge or diverge?
Converge.
Yes, it will converge. So in a geometric series, if the ratio that it's multiplying by each time is less than 1, if the absolute value of the ratio is less than 1, then it will converge. If the ratio is less than 1 of what it's multiplying by, it will converge. So this will converge, which is why they asked us to find the sum. So converges by geometric series. Test. And now let's just state what it does converge to. So S, the sum, will equal A over 1 minus R. So A, what's our A value?
2.
Yes, A is going to be 2. It's the very first value. So we have 2 over 1 minus, here R is the negative 1/2. Negative 1/2. And could you stop right there? Yes, you could, but this one's not that hard to finish. I just multiply top and bottom by 2 over 2. And when I multiply the top by 2, that gives me 4. When I multiply the bottom by 2, well, first off, that's a minus, and negative becomes a plus. 2 times that 1 would give you 2. And 2 times 1/2 would give you 1. So you'd end up with 2 plus 1 in the denominator. So 3. So 4/3 would be the sum. Okay, and so this free response question with these 5 parts was a good example of a way that they could ask a whole bunch of different things, test a lot of different concepts, all in one multi-part question. Now that we know a little more about the exam, I don't think it'll be exactly like this. And I just say that because the guy who made this example, he made these ones that you have as soon as we found out about it being 2 questions and 45 minutes. So the idea of all 4 of these ones, title of the BC questions 1 through 4, they all should take about 20 to 22 minutes, each one of them. they were each meant to be what would be half of the length of time, what one question could be if they were even. But they have what we have now found out that the two questions will not be, one will be 25 minutes, one will be 15. But I guess the longer one could be a little like these, maybe. And yes, Sean, the keys will be posted like I did this week. I'll post the keys on Tuesday. I'll post the keys next Tuesday. Oops. Okay, well, it has been a while. It's 2:10. And have a great day. Again, keys will be posted Tuesday. It sucks that I won't see y'all probably until graduation in July. But have a great day.
Wait, for the
Trevor.
stuff that we're turning in today, do we take a picture of like every page and then like send it?
I mean, not every page is necessary.
Oh well.
Uh,
I did that at like 1:30.
just show that you did stuff, I guess.
Okay.
Prove to me that you're working.
All right.
Hey, Mr. Hunter, can you go over one of them on the, one of the packets real quick? The A through Z.
Which number?
It's just the last one, Z, setting up an integral for volume by revolution.
Well, that definitely could be on this year's exam, so let me look at that real quick. Oh, that's going to be a washer method, right? Expression of volume, one or more integrals that gives volume when the region's bounded. Looking at the line y equals 5. And we're looking at that picture up above. Yeah, so quickly show you something with that. So looking at this, Z set up a denominator expression involving one or more integrals that gives the volume in the region is revolved around y equals -5. So revolving around a horizontal line, x is still going to be our variable. Don't have to do anything weird with that. But we have these two functions here. Where they tell us what those were? Oh, that's g of x and h of x. H of x, they already gave us up here. Okay, so you should have already you already have h of x somewhere. We're going from 1 to 3. Oh, from 1 to 3, h is this quadratic. Okay, so h is that quadratic from 1 to 3. And you already found k way earlier in the packet. And then d function on top is this sine function they gave you right here. Okay, so to just very quickly go over what they're intending here. Go to this page right here. So the picture, what we kind of have, we got two functions right here. We got d of x on top. We got h of x on bottom. Very rough sketch of what they have. Okay, and then we are wanting to revolve it around y equals 5, which is way up there. Around y equals 5, which is way up there.
-5.
Oh, -5? Okay, -5. Same idea though, just I drew it in the wrong spot. We want to revolve around y equals -5, which is down here. Y equals -5 does not intersect with that at all. Okay, so it's revolving around that y equals -5. And so we want to use volume formula washer method. So it'll be the integral from the beginning x value to the ending x value. Put pi out front of capital R squared minus lowercase r squared dx, where capital R represents the, let me change colors. Capital R here, the axis of revolution is this y equals -5, blue dashed line. So capital R is going to be this the distance from here all the way to dx. And then lowercase r is the distance between h of x and that line. Which is going to mean that capital R is going to be dx of x minus -5, and lowercase r is going to then be h of x minus -5. And so if we plug those in there, that'd be pi integral from a to b of d of x plus 5 squared minus parentheses h of x plus 5 squared dx. And they you already have the h of x and d of x. And then a and b, that's beginning and ending points, where that's a right there and that's b right there. So that's how you would set up that integral.
Okay, because the key had like, it was like that, except it was negative d of x minus 5, and then negative h of x minus 5.
That's essentially the same thing, though.
Okay, because they're squared and it's
Yeah.
the same thing.
Because when you square it, it's going to undo the negative.
Okay.
Yeah. You'd get the same answer as what I wrote. I think my way probably makes a little more sense, though.
Also, I think part y was slightly different. When I was looking at the key, it had the d of x equation was slightly different. I saw on your page it was the same as what I have.
Wait, part y?
Yeah, inside the parentheses, it has a plus pi over 2. On our paper, it's plus 1/2.
Wait, where?
In the d of x equation, they have a plus pi over 2 inside there. Ours is plus 1/2.
Do they have like pi times everything? Oh yeah, that is different. No, they don't.
So if we solved it with the 1/2, is that just fine?
Yeah, perfectly fine.
Okay.
Okay, well, let's be done for today.
Bye.
Bye, guys.
See ya.
See ya.